Okay, more probability examples. Suppose you're rolling a pair of dice. They might be the same color or they might be different colors. It's easier to see that there are 36 possible ways they could come up if you make them different colors. So for example, a 2 on the red die and a 1 on the green die would be a different outcome than getting a 1 on the red and a 2 on the green. So altogether there are 36 different ways that a pair of dice could come up. 36 possible outcomes to the experiment where you roll a pair of dice. What's the probability of rolling doubles? Well, let's count how many ways that can happen. 1, 2, 3, 4, 5, or 6. You could get double ones, double twos, threes, fours, fives, or sixes. So there's 6 ways that the dice could come up doubles out of 36 ways they could come up altogether. So the probability that you would roll doubles when you roll a pair of dice would be 6 over 36. Now, as a fraction, that's not in lowest terms, so if you reduce it to lowest terms, it would be 1/6. As a decimal, it would be 0.167, or as a percent, it would be 16.7%. So your chances of rolling doubles are 1/6, or 0.167, or 16.7%. What about rolling dice that total 12? How many ways could that happen? Well, there's only one of these outcomes where the dice add up to 12. So the probability is 1 over 36, which would be 0.028 or 2.8%. That's something that would happen about 2.8% of the time if you rolled the dice over and over again. So on any individual roll, you could say there's a 2.8 probability that you would get a 12. What about the probability of rolling dice that total 8? Well, how many different ways could that happen? Out of these 36 outcomes, how many of them add up to 8? Well, let's see. There's 1, 2, 3, 4, 5. 6 and 2, 5 and 3, 4 and 4, 3 and 5, 2 and 6. So the probability of rolling a total of 8 would be 5 over 36, which would be 0.139 or 13.9%. What's the probability of rolling a 3 on at least one of the dice? What's the probability that when you roll a pair of dice, you get a 3 showing on at least one of the dice? So count how many different ways that could happen. Out of these 36 possible outcomes, how many of them have this event being true, where you've got a 3 on at least one of the dice? Well, let's see. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the probability that you would get a 3 on at least one of the dice is 11 over 36. 11/36, which is 0.306 or 30.6%. What's the probability that you roll dice that total 13? Well, let's go through and count all the different ways that could happen. And the number of different ways that can happen would be 0. There are none of these outcomes where the dice add up to 13. So the probability there would be 0 over 36, which would just be 0. And remember we said when we've got something that can't possibly happen, something that never happens, the dice never total 13, that's when the probability is 0. Okay, another example. This time we are picking a card from a regular deck of 52 cards. And if you don't play cards much, a deck of cards looks like this. The cards are divided up into 4 suits: clubs, diamonds, hearts, and spades. And in each suit there's an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. the clubs and spades are black and the diamonds and hearts are red. So every card is either a red card or a black card. Now, what's the probability that if you pick one card out of the deck, you'll pick a red card? Well, how many ways could that happen? 26 out of 52 in all. So the probability of picking a red card would be 26 over 52. Now, in lowest terms, that fraction would just be 1 over 2, 1/2, which makes sense because half of the cards are red cards. So the probability of picking a red card is 1/2. You could also write that as 0.5 or 50%. What's the probability of picking a spade? Well, how many different ways could that happen? 1, 2, 3, 4, 5, 13. So the probability is 13 over 52. If you reduce that fraction to lowest terms, it's 1 over 4, 1/4, which would be 0.25 or 25%. What about picking an 8? How many ways could that happen? 4. You can get the 8 of clubs, the 8 of diamonds, the 8 of hearts, or the 8 of spades. So the probability of picking an 8 would be 4 over 52, which reduces to 1/13. As a decimal, that's 0.077. As a percent, that's 7.7%. What's the probability of picking a face card, which means either a jack, queen, or king? How many of those are there? How many ways could that happen? 12. So the probability is 12 over 52. In lowest terms, that would be 3/13. As a decimal, it would be 0.231. As a percent, it would be 23.1%. And what about picking a heart or the queen of spades? Well, let's count all the different ways that could happen. Out of all 52 cards, which ones would have you saying, yes, the card I picked is either a heart or the queen of spades? Well, let's see. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So if you're playing some sort of game where you win if you pick either a heart or the queen of spades, your probability of that happening would be 14 over 52, which is equivalent to 7 over 26, or 0.269, or 26.9%. Next example. If I put a $100 bill, a $10 bill, and 98 $1 bills in a sack, and you reach in and pick one without looking, what is the probability that you'll get the $100 bill? Okay, so how many ways could that happen? 1. Out of how many possible outcomes in all? Well, there's 100 bills in there. You could get any one of those, so the probability is 1 over 100, otherwise known as 0.01 or 1%. You got a 1% chance of getting that $100 bill. What's the probability that you'll get the $100 or the $10 bill? Well, now there's 2 possible ways that could happen. Namely, you could get the $100 bill or you could get the $10 bill. So with 2 ways of that happening out of 100 in all, the probability there is 2 over 100. 2 divided by 100 would be 0.02, or as a percent, that would be 2%. At a certain college, of the 729 students enrolled, 317 of them are male. Now assume in this example that everybody is one or the other. Everybody at this college identifies as being either male or female. So the probability that a randomly chosen student is male would be 317 out of, or over, or divided by 729. If you divide that, it comes out to be, when I round to 3 decimal places, 0.435. As a percentage, that would be 43.5%. 43.5% of the students are male. So that means there's a 43.5% probability that any one randomly chosen student would be one of the male students. What's the probability that a randomly chosen student is female? Okay, remember I said everybody's either one or the other. So if we take how many there are in all and subtract how many of them are male, we get how many of them are female. So 317 males, the other 412 are female. So the probability that the one we select is female would be 412 over 729, which is 0.565 or 56.5%. Now notice something here. We already found that there was a 0.435 probability that a student is male. If we take 1 minus 0.435, we get 0.565. Or in percents, 100% minus 43.5% equals 56.5%. So if we start with all 100% of the students and subtract off the 43.5% of them that are male, we are left with the 56.5% of them who are female. And this is an example of where the probability that a student is female would be equal to 1 minus the probability that that student is not female. In other words, that that student is male. So this is an example of a general rule that comes in handy a lot, that the probability of something not happening is 1 minus the probability of it happening, or vice versa. The probability of something happening is 1 minus the probability of something not happening. So when we talk about something not happening, that gets into what's called complementary events. If we use a letter like E to stand for some event that might happen or it might not happen, then an E with a line over it, pronounced E complement, or maybe just E bar, would stand for the complement of that event. And that's the notation that our book uses, but if you read other statistics or probability books, other books sometimes use an E prime or an EC instead of E bar. Different notations for the same thing, but we'll use the bar. So E bar or E complement is what happens whenever E does not happen. If you think of an event as a set of outcomes, E complement is the set of all the events that are not part of E. So for example, if your experiment is rolling a die, and you're talking about the event of rolling a 6, the complement of that would be not rolling a 6, rolling something that's not a 6, which means it's either 1, 2, 3, 4, or 5. The complement of rolling a 5 or a 6 would be where that doesn't happen, which means you rolled a 1, 2, 3, or a 4. The complement of rolling an even number would be rolling a number that's not an even number, which means it's an odd number. If your experiment is rolling 2 dice, the complement of rolling doubles would be not rolling doubles, rolling dice that don't match. The complement of rolling dice that total 8 would be rolling dice that don't total 8, that add up to something other than 8. And the complement of rolling a 3 on at least one of the dice would be where that doesn't happen, where neither of the dice is a 3. It's got to be one or the other. So either this happens or the complement of this happens. If this happens, the complement didn't. If the complement happened, the original event didn't. So the rule here is that the probability of something not happening is equal to 1 minus the probability of it happening, and vice versa. So all three of these equations are algebraically equivalent. You could just rearrange one of these to get another one. But in words, that means that the probability that an event does not occur is equal to 1 minus the probability that it does occur. And that also means that the probability that an event does occur is equal to 1 minus the probability that it does not occur. I'm going to end this video here and come back in the next one with some specific examples of this.